Look up at the night sky, and what do you see? A scattering of stars, perhaps a few distant galaxies, pinpricks of light against an endless dark. But what if I told you those specks of light are just the visible threads of something far grander? Hidden from our eyes lies an unimaginably vast structure, a delicate yet powerful network stretching across the entire universe. This is the cosmic web, an intricate lattice of galaxies, dark matter, and invisible forces, all bound together in a silent, gravitational ballet. It's the universe's hidden architecture, the scaffolding upon which everything we know is built, and today we're about to unravel its secrets. Think of the cosmic web as the universe's ultimate connect-the-dots puzzle. Each galaxy, each cluster, is a single point in a pattern so enormous it defies comprehension. Some of these structures span hundreds of millions of light years, weaving through the void like invisible highways. But here's what's truly mind-bending. This web isn't static. It's alive with motion, with galaxies drawn toward one another by forces we're only beginning to understand. Dark matter tugs at them like unseen puppet strings, while the fabric of space itself bends and warps under the weight of these colossal structures. What we're seeing isn't just a snapshot, it's a dynamic, ever-evolving masterpiece painted across the canvas of time. So how do we even begin to map something so vast, so hidden? That's where the real adventure begins. Over the next 28 revelations, we'll journey through the most astonishing cosmic webs ever discovered, structures so immense they rewrite our understanding of the universe. We'll witness galaxies strung like pearls on invisible threads, encounter voids so empty they'll make your jaw drop, and uncover the forces that sculpted the cosmos into the shape we see today. This isn't just science, it's a detective story on the grandest scale, where every clue brings us closer to answering the biggest questions of all. How did the universe take this shape? And what does it tell us about where we're headed? Strap in, because by the end of this journey, the night sky will never look the same to you again. Hidden in the vast darkness between constellations lies something that defies our wildest expectations: the Great Wall. Not made of brick or stone, but of galaxies, thousands upon thousands of them, strung together in a filament so immense it would take light 500 million years just to travel from one end to the other. Picture this: if our Milky Way were a single grain of sand, the Great Wall would stretch longer than the entire Sahara Desert. It's not just big, it's one of the largest structures ever discovered in the observable universe, a cosmic skyscraper built by gravity itself. What makes this discovery so astonishing isn't just its scale, but what it reveals about the universe's blueprint. When astronomers first spotted the Great Wall in the 1980s, it shattered existing theories about how matter should be distributed in space. Before then, scientists assumed galaxies were scattered randomly, like stars sprinkled across the night sky. But the Great Wall proved otherwise. Galaxies aren't just floating freely, they're linked, drawn together in vast networks by forces we can't even see. This is where dark matter comes into play, the universe's invisible architect. Like scaffolding behind a building's walls, dark matter's gravitational pull molds these colossal structures, guiding galaxies into place over billions of years. Yet the Great Wall isn't just a relic of the past, it's still evolving. Gravity continues to tug at its galaxies, pulling some closer while others drift toward neighboring filaments. Somewhere in that vast web, entire clusters are colliding, merging into even larger superstructures. And here's the real wonder: we're seeing this unfold in slow motion. Because of the mind-boggling distances involved, the light reaching our telescopes today shows us the Great Wall as it was hundreds of millions of years ago. By the time we observe its next cosmic dance, the structure may have already transformed into something even grander. So what does this mean for our place in the universe? The Great Wall forces us to confront a humbling truth. We're not just living in a galaxy, we're part of something far larger, a tapestry of matter woven across space and time. And if structures like this exist, what else lies hidden in the darkness, waiting to be discovered? The Great Wall isn't just a landmark, it's a signpost pointing us toward deeper mysteries in the cosmic web. Just when we thought the Great Wall had redefined cosmic scale, along came something even more staggering: the Sloan Great Wall. Discovered in 2003, this behemoth stretches over 1.4 billion light-years across the universe, making it one of the longest known structures in existence. To put that into perspective, if you could travel at the speed of light, a mind bending 671 million miles per hour, it would still take you more than 1 billion years to traverse this cosmic colossus from end to end. What makes the Sloan Great Wall so fascinating isn't just its jaw-dropping size, but the way it was discovered. Unlike stumbling upon a bright galaxy or a swirling nebula, finding this structure required something far more meticulous: the Sloan Digital Sky Survey. This ambitious project mapped millions of galaxies with unprecedented precision, revealing patterns invisible to the naked eye. And there, hidden in the data, was the Sloan Great Wall, not a random scattering of galaxies, but a meticulously aligned chain, like beads on an unimaginably long string. This discovery gave us something even more valuable than a new cosmic record. It handed us a clue about how the universe organizes itself. Those galactic filaments aren't accidental. They follow the hidden scaffolding of dark matter, the unseen force that shapes the cosmos. Think of it like this: if galaxies were cities, dark matter would be the sprawling highway system connecting them, invisible but essential. The Sloan Great Wall shows us that the universe doesn't just expand randomly, it builds, it structures, it connects. Yet for all its grandeur, the Sloan Great Wall also poses a cosmic riddle. According to our current understanding of the universe, structures this massive shouldn't exist. The laws of physics suggest there hasn't been enough time since the Big Bang for gravity to pull matter into such an enormous configuration. So does that mean our theories are missing something? Or is the Sloan Great Wall a rare, almost impossible fluke? Either way, this titanic structure forces us to rethink what we know about the universe's birth and growth. And here's the thrilling part: this isn't the end of the story. As our telescopes grow more powerful and our surveys more detailed, who knows what other colossal structures we might uncover? The Sloan Great Wall isn't just a wonder to admire, it's a challenge, a cosmic puzzle waiting to be solved. And with every new discovery, we're not just mapping the universe, we're deciphering its deepest secrets. If the Sloan Great Wall left you awestruck, prepare for something that redefines the very meaning of large scale. Meet the Hercules Corona Borealis Great Wall, a structure so vast it makes previous cosmic giants look like specks. Stretching an almost incomprehensible 10 billion light-years, this behemoth isn't just breaking records, it's shattering our understanding of how the universe organizes itself. To grasp that scale, consider this: if our entire Milky Way galaxy were the size of a coffee cup, the Hercules Corona Borealis Great Wall would span the width of the Pacific Ocean. What makes this discovery so revolutionary isn't just its size, it's the timing. When astronomers first identified it in 2013, it sent shockwaves through the scientific community. Why? Because it directly challenges one of cosmology's foundational ideas, the cosmological principle. This principle states that, on large enough scales, the universe should appear roughly uniform no matter where you look. But here's the catch: the Hercules Corona Borealis Great Wall isn't uniform at all. It's a glaring exception, a cosmic anomaly so massive it forces us to ask, is our understanding of the universe's structure fundamentally incomplete? Imagine the universe as a freshly baked loaf of bread. According to the cosmological principle, the distribution of raisins representing galaxies should be fairly even throughout. But the Hercules Corona Borealis Great Wall is like finding a single, gigantic clump of raisins spanning half the loaf. How did such an extreme concentration of matter form? Current theories suggest it might be a relic of the universe's earliest moments, a frozen ripple from the Big Bang itself. Some researchers even speculate that structures this colossal could be the fingerprints of exotic physics we haven't yet discovered. Perhaps even evidence of parallel universes brushing against our own. Yet for all its mystery, this wall isn't just a scientific puzzle, it's a time machine. Because light takes so long to travel such vast distances, when we observe it, we're peering back to when the universe was less than half its current age. That means we're not just seeing a structure, we're witnessing a snapshot of cosmic adolescence, a moment when the universe was still assembling its largest features. And here's the twist: by now, billions of years later, this wall may have evolved into something even stranger, a possibility that keeps astronomers awake at night. So what does this mean for the future of cosmology? The Hercules Corona Borealis Great Wall isn't just an outlier, it's a beacon illuminating the gaps in our knowledge. Every time we push the boundaries of observation, the universe seems to reveal structures more bizarre than we ever imagined. If something this enormous could exist without us predicting it, what other cosmic wonders are still waiting in the dark? One thing's certain: the universe's grandest designs are far from finished surprising us. We may think of our Milky Way as vast beyond measure, but zoom out far enough, and it becomes a single speck in something far grander, the Laniakea Supercluster. This sprawling celestial metropolis, whose name means immense heaven in Hawaiian, is home to over 100,000 galaxies, all bound together by the invisible threads of gravity. Picture a cosmic city where galaxies are the buildings, and dark matter forms the streets, a network so vast it would take light 500 million years just to cross from one side to the other. And here's the humbling part: we're not just observers of this structure, we're residents carried along its currents like leaves in a river. What makes Laniakea so extraordinary isn't just its scale, but the way it moves. Every galaxy within it, including our own, is drifting toward a mysterious gravitational focal point known as the Great Attractor. Think of it as a cosmic whirlpool, pulling everything in its vicinity toward an unseen center. For decades, this region remained hidden behind the dust and stars of our own galaxy's disk, like a mountain obscured by fog. But with advanced infrared telescopes, we've begun to peel back the veil, revealing a dense cluster of galaxies with a gravitational pull so strong it bends the very fabric of space around it. This discovery reshapes our cosmic address. We're no longer just orbiting a star in the Milky Way, we're part of a supercluster, a family of galaxies all flowing toward the same destination. And the highways they travel, those are the filaments of the cosmic web, vast tendrils of dark matter that guide galaxies along their paths. It's like watching traffic on a freeway, except instead of cars, it's entire galaxies, all moving in unison across billions of years. Yet Laniakea isn't just a static map, it's a snapshot of an ever-changing universe. The supercluster itself is drifting, pulled by even larger structures beyond its borders. Somewhere in the distant future, it may collide with another supercluster, merging into something even more immense. And the Great Attractor, it's just one of many such focal points in the cosmos, each a reminder of how much we still don't know about the forces shaping our universe. So what does this mean for us? Laniakea forces a profound shift in perspective. We're not just living in a galaxy, we're part of a vast dynamic structure, one thread in a tapestry that stretches across the observable universe. And as we continue to map these cosmic flows, we're not just charting space, we're tracing the story of everything, one gravitational ripple at a time. The Pisces-Setus supercluster complex isn't just another entry in the cosmic record book, it's a masterclass in the universe's architecture. Imagine a sponge, its intricate network of holes and fibers magnified to cosmic proportions, and you'll start to grasp this colossal structure. Spanning over 1 billion light-years, it's not just the sheer size that astonishes, it's the way galaxies cluster along delicate filaments, weaving around voids so empty they'd make the deepest reaches of space feel crowded. These voids aren't just gaps, they're cosmic deserts, regions where matter is almost entirely absent, some stretching hundreds of millions of light-years wide. What makes this supercluster complex so special isn't just its scale. It's the story it tells about the universe's adolescence. When astronomers study its filaments, they're peering back to a time when the cosmos was still assembling its largest structures. The galaxies here aren't randomly scattered. They're strung along these tendrils like dew on a spider's web, tracing the invisible scaffolding of dark matter. And the voids, they're just as critical. These enormous bubbles of near-nothingness act as cosmic mirrors, reflecting the echoes of the Big Bang itself. By measuring how light bends around their edges, we can map the distribution of matter with astonishing precision, uncovering clues about how the universe grew from a fiery infancy into the web we see today. But the Pisces-Setus complex isn't just a relic, it's still evolving. Gravity continues to sculpt its filaments, drawing galaxies closer together while the voids expand, stretching the cosmic web even thinner. Somewhere in that vast network, entire clusters are merging, their collisions sending ripples through the fabric of space-time. And here's the twist, because light takes so long to reach us, we're seeing this dance as it happened billions of years ago. By now, the structure may have transformed into something unrecognizable, a reminder that the universe is never static. This supercluster complex also holds a key to one of cosmology's biggest puzzles. How did matter clump together so quickly after the Big Bang? The answer might lie in those filaments. Computer simulations suggest they're the universe's original highways, channels where matter flowed like water through cracks in ice, pooling into the dense nodes we see as galaxy clusters today. If that's true, then Pisces-Setus isn't just a structure, it's a fossil, preserving the universe's earliest building plans. Yet for all we've learned, this complex still guards its secrets. Why do some voids stay eerily empty while others sprout new galaxies? How do filaments maintain their delicate balance, resisting the pull of nearby superclusters? Each question pulls us deeper into the cosmic web's mysteries, reminding us that even the largest structures in the universe are just pieces of a puzzle we're only beginning to solve. And as our telescopes grow sharper, who knows what other wonders or contradictions we'll find woven into this billion-light-year tapestry. Among the cosmic web's grand structures, some of the most puzzling aren't the dense clusters or glittering filaments, they're the staggering absences. Enter the Boötes void, a cosmic emptiness so vast it redefines our understanding of space itself. Picture a sphere of darkness stretching 330 million light-years across, containing only a handful of galaxies where thousands should exist. If our Milky Way sat at its center, the nearest major galaxy would be so distant, its light would take tens of millions of years to reach us, a solitude almost beyond comprehension. This isn't just an empty patch of sky, it's a fundamental challenge to cosmology. According to standard models of the universe's evolution, matter should be distributed far more evenly than this. The Boötes void is like finding a swimming pool where someone forgot to add water. Its existence forces us to reconsider how gravity sculpted the early cosmos. Some theories suggest it might be the imprint of an ancient collision between bubble-like regions in the infant universe, while others propose even wilder ideas. Could this void be evidence of a neighboring universe tugging at ours, leaving behind a fingerprint in the form of nothingness? What makes the Boötes void truly eerie is how galaxies behave at its edges. Observations show they're not just sitting idly, they're streaming away, as if repelled by some unseen force. This motion hints at the void's hidden influence, warping space-time like a reverse gravity well. Imagine throwing a pebble into a pond, only to watch the ripples flow inward instead of outward. That's the kind of counterintuitive physics we're dealing with here. And because light from the void's far side takes hundreds of millions of years to reach us, we're seeing it as it was when dinosaurs still roamed Earth, adding another layer of mystery to its evolution. Yet for all its strangeness, the Boötes void isn't entirely empty. The few galaxies it does contain are oddly isolated, like lone travelers crossing an endless desert. Studying these galactic survivors has revealed something unexpected. Many are younger and bluer than their counterparts in denser regions, suggesting voids might be cosmic nurseries for certain types of star formation. It's as if the universe, in its relentless creativity, found a way to paint with light even in the darkest corners. So what does this mean for our cosmic maps? The Boötes void is more than a curiosity. It's a boundary marker showing us where our theories hit their limits. If structures this empty can exist, what other impossibilities might we discover as our telescopes peer deeper? Whether it's evidence of multiverses, unknown physics, or simply nature's capacity for surprise, one thing's certain: the universe reserves its most profound lessons not just in the glittering crowds, but in the silent spaces between. Before the Sloan Great Wall or the Hercules Corona Borealis structure rewrote the cosmic record books, there was the CFA2 Great Wall, a discovery so groundbreaking it changed astronomy forever. In the 1980s, when most scientists still pictured galaxies as randomly scattered islands in space, this colossal filament of galaxies stretched across the sky like a crack in the cosmic egg. At nearly 500 million light-years long, it wasn't just big, it was proof that the universe had a hidden blueprint, one we were only beginning to decipher. What made the CFA2 Great Wall revolutionary wasn't just its size. It was the way it forced astronomers to rethink everything. Before its discovery, the prevailing view was that galaxies should be distributed fairly evenly throughout space, like raisins in a loaf of bread. But when researchers from the Harvard-Smithsonian Center for Astrophysics, the CFA in its name, mapped this region, they found something startling. Galaxies weren't sprinkled randomly, they were clumped together in vast sheets and filaments with enormous voids between them. It was as if someone had taken a paintbrush and drawn bold, sweeping strokes across the cosmos, leaving dark gaps where nothing seemed to exist. This was the moment the cosmic web went from theory to reality. The CFA2 Great Wall became the Rosetta Stone of large-scale structure, showing us that dark matter's gravitational pull had sculpted the universe into an intricate network. Think of it like watching iron filings align along the invisible lines of a magnetic field, except here, the filings were entire galaxies, and the magnet was the unseen hand of dark matter. For the first time, we had tangible evidence that the universe wasn't just expanding, it was organizing itself on scales we'd never imagined. But here's where the story gets even more fascinating. Unlike later discoveries made with advanced digital surveys, the CFA2 Great Wall was found using painstaking manual observations. astronomers poring over photographic plates, marking galaxies one by one. It was cosmic cartography in its purest form, a testament to human curiosity and persistence, and the payoff was enormous. This wall didn't just hint at dark matter's role, it revealed how galaxies move within these vast structures, flowing along filaments like water through riverbeds pulled by gravity's relentless tide. Today, the CFA2 Great Wall might seem modest compared to the titans we've since uncovered, but its legacy is immeasurable. It taught us to see the universe not as a scatter of stars, but as a living, evolving web, one we're still learning to navigate. And as we peer deeper into space with ever more powerful tools, we're standing on the shoulders of this discovery, tracing the threads it first revealed, following them deeper into the cosmic dark. Just when we thought we understood the cosmic web's grand design, astronomers stumbled upon something that defies all expectations: the dark flow. Picture this: hundreds of galaxy clusters, each containing thousands of galaxies, all drifting in the same direction like leaves caught in a cosmic river. But here's the catch: there's no visible force pulling them. No supercluster, no great attractor, nothing in the observable universe powerful enough to explain this synchronized motion. It's as if space itself has a current, one we can't see or fully comprehend. This discovery didn't just raise eyebrows, it sparked a firestorm in cosmology. When NASA Wilkinson Microwave Anisotropy Probe first detected the dark flow in 2008, it measured these clusters moving at staggering speeds, over 2 million miles per hour, toward a single patch of sky near the constellations Centaurus and Vela. The kicker: that region doesn't contain any known mass large enough to justify such movement. Gravity, as we understand it, simply can't account for this. So what's really going on? One theory pushes the boundaries of physics itself. Some researchers suggest the dark flow might be a relic from the universe's infancy, a ripple frozen in time from the moments just after the Big Bang. Imagine stretching a rubber sheet and letting it snap back. The vibrations linger. In this case, the snap was the universe's explosive birth, and the dark flow could be its echo, still tugging at galaxies billions of years later. But there's an even wilder possibility. What if this motion isn't coming from our universe at all? That's where the multiverse hypothesis enters the picture. If other universes exist beyond our cosmic horizon, their gravitational pull might be leaking into ours, dragging these clusters toward something we can't see. Think of it like standing near an invisible magnet. You can't see it, but you feel its pull. The dark flow could be our first tantalizing hint that we're not alone in the greater fabric of reality. Of course, not everyone's convinced. Skeptics argue it might be a measurement error or an artifact of incomplete data, a cosmic illusion that will fade with better observations. Yet the mystery only deepens when we look at the scale of this phenomenon. The dark flow isn't just local, it stretches over billions of light years, encompassing clusters so distant their light has traveled for eons to reach us. That means whatever's causing this isn't just powerful, it's operating on a scale that dwarfs even the largest known structures in the universe. And because light takes so long to cross these distances, we're seeing the dark flow as it was in the distant past. By now, its source, whether a relic, another universe, or something entirely unknown, may have evolved beyond recognition. What makes the dark flow so electrifying isn't just the scientific debate, it's the profound questions it forces us to confront. Are we missing a fundamental piece of physics? Is the cosmological principle, the idea that the universe should look roughly the same everywhere, in need of revision? Or have we truly brushed against the edge of the observable, where the rules we know start to bend? The dark flow doesn't just challenge our models, it invites us to imagine a cosmos far stranger and far more interconnected than we ever dared to dream. Among the faint whispers of the Big Bang's afterglow, one anomaly stands out like a cosmic sore thumb: the cold spot. Nestled within the cosmic microwave background, that ancient light from the universe's infancy, this region is colder than its surroundings by a margin that defies easy explanation. It's not just a slight dip in temperature. This spot spans nearly 2 billion light-years, a chilling void in the otherwise uniform sea of microwave radiation. To understand why this matters, imagine pressing your hand against a warm window pane and finding one spot inexplicably icy to the touch. Something isn't right, and scientists are scrambling to figure out what. Theories about the cold spot's origins read like a sci-fi plot. One tantalizing idea suggests it might be evidence of a collision with another universe, a bruise left behind when our cosmos bumped into a neighboring reality in the multiverse. Picture two soap bubbles brushing against each other in a sink. The point of contact would drain energy, leaving behind a cooler patch. If true, this would be our first glimpse beyond the edges of our own universe, a crack in the cosmic egg revealing something unimaginable on the other side. But not everyone's convinced. Skeptics argue the cold spot could simply be a supervoid, an enormous region of space with far fewer galaxies than average. Less matter means less gravity, which in turn allows light passing through to lose energy, cooling as it stretches across the void, a phenomenon known as the integrated Sachs-Wolfe effect. Yet there's a problem with the supervoid explanation. While astronomers have found voids in the cold spot's general direction, none are large or empty enough to account for the temperature drop. It's like blaming a snowstorm on a single ice cube. The scale just doesn't add up. This leaves cosmologists at a crossroads. If the cold spot isn't a void and isn't proof of a multiverse, what else could it be? Some propose it's a rare statistical fluke, a cosmic roll of the dice that just happened to leave one corner of the universe unnaturally chilly. Others wonder if it's a sign of exotic physics we haven't yet discovered, a wrinkle in the fabric of space-time itself. The cold spot's mystery deepens when we consider its implications. If it is a multiverse fingerprint, it would upend our understanding of reality, proving we're part of something far grander than this single universe. But even if it's something else entirely, its existence challenges the cosmological principle, the idea that, on large scales, the universe should look roughly the same everywhere. A structure this anomalous suggests the cosmos might be more unpredictable, more textured than we ever imagined. What makes this enigma so compelling isn't just the scientific debate, it's the sheer audacity of the questions it forces us to ask. Are we seeing the shadow of another universe? Is the cold spot a flaw in our models, or a flaw in the universe itself? Every new observation, every sharper map of the cosmic microwave background brings us closer to an answer. And whether the solution is mundane or mind-bending, one thing's certain: the cold spot reminds us that even in the oldest light we can see, the universe still has secrets left to tell. Tucked away behind the blinding glow of our own Milky Way lies a cosmic giant we almost missed: the South Pole Wall. Stretching an astonishing 1.4 billion light-years across the southern sky, this galactic filament remained hidden for so long because our own galaxy's dust and stars formed a celestial curtain, blocking our view. It's like trying to spot a mountain range through a snowstorm. Until recently, we had no idea it was there at all. But thanks to cutting-edge redshift surveys, which measure how light from distant galaxies stretches as the universe expands, astronomers finally pulled back the veil, revealing one of the largest structures ever found in our cosmic neighborhood. What makes the South Pole Wall so remarkable isn't just its size. It's the way it forces us to confront how little we truly know about the universe's architecture. Even in an age of space telescopes and deep field imaging, colossal structures like this can still lurk undetected. masked by the very galaxy we call home. Imagine spending your whole life in a house with boarded-up windows, only to one day pry them open and discover a sprawling city just outside. That's the scale of this revelation. And if something this massive could stay hidden for so long, what else might be waiting in the shadows? Mapping this wall required more than just pointing telescopes at the sky. Researchers had to piece together its structure by analyzing the subtle redshifts of thousands of galaxies, tracing their movements like dots in a connect-the-dots puzzle spanning billions of light years. The result, a filament so vast it rivals the Sloan Great Wall, weaving through the cosmic web like a hidden backbone. But here's the twist. Unlike other giant structures, the South Pole Wall isn't just a distant relic. It's close enough to influence the motion of our own local group of galaxies, tugging at us with its gravitational pull. Yet for all its grandeur, the South Pole Wall raises as many questions as it answers. Why does it align so neatly with other nearby filaments? Could it be part of an even larger structure we haven't mapped yet? And most tantalizing of all, how many more of these cosmic giants are still hiding behind the Milky Way's glare? Every time we develop new tools to peer deeper into the universe, we uncover another layer of its complexity, another reminder that the cosmic web is far richer and more intricate than we ever imagined. This discovery isn't just about adding another entry to the catalogue of cosmic wonders, it's a humbling lesson in perspective. The South Pole Wall shows us that even in an era of advanced astronomy, the universe still holds secrets just out of sight, waiting for the right moment and the right technology to reveal them. And as we continue to map these hidden structures, we're not just filling in blanks on a chart. We're rewriting the story of how the universe organizes itself, one filament at a time. Deep in the cosmic archives, where light has traveled for over 10 billion years to reach us, lies a scene of celestial chaos, the Spiderweb Galaxy. This isn't just one galaxy, but a swirling maelstrom of dozens, perhaps hundreds, caught in the act of merging into what will eventually become one of the universe's most massive structures. Picture a spider's web glistening with dew, except each droplet is an entire galaxy, and the silk threads are the invisible strands of dark matter pulling them together. This is the cosmic web in its most violent, dynamic form, a snapshot of the universe's adolescence frozen in time. What makes the Spiderweb Galaxy so extraordinary isn't just its scale, it's the timing. We're witnessing this collision as it happened when the universe was just 3 billion years old, a mere toddler by cosmic standards. Back then, galaxies weren't the orderly spirals and ellipticals we see today. They were smaller, wilder, and constantly crashing into one another like bumper cars in the dark. The Spiderweb captures this era perfectly, with galaxies swarming toward a central massive galaxy like moths to a flame, drawn in by gravity's irresistible pull. Infrared observations reveal something even more astonishing. These galaxies aren't just merging. They're drowning in a sea of newly forming stars, ignited by the sheer turbulence of their collisions. But here's where the story takes a fascinating turn. Unlike modern galaxy clusters, where mergers are rare and orderly, the Spiderweb shows us a universe still under construction. The galaxies here aren't just passively falling together, they're feeding a monstrous central galaxy, which grows by devouring its neighbors. Think of it like a cosmic whirlpool, with smaller galaxies spiraling inward, their gas and stars being stripped away in vast streams. This isn't destruction, it's transformation on a scale we can barely comprehend. And hidden within this chaos is a clue to one of astronomy's biggest mysteries, how the universe's most massive galaxies grew so large so quickly. The Spiderweb also gives us a front row seat to another cosmic spectacle, the birth of a galaxy cluster. Today, clusters like Coma or Perseus are filled with thousands of galaxies bound together by gravity. But in the spiderweb, we're seeing the raw materials of such a cluster coming together for the first time. The dark matter scaffolding is already in place, and the galaxies are just beginning to settle into their roles, some destined to become bright central giants, others fading into the background as faint satellites. It's like watching the foundation of a skyscraper being poured, knowing that billions of years later it will dominate the skyline. Yet for all its violence, the spiderweb holds a surprising delicacy. Hubble images show delicate filaments of gas stretching between galaxies, not just the thick ropes of dark matter we expect, but wispy bridges of hydrogen and helium, the universe's raw ingredients. These filaments are the true cosmic web, the highways along which matter flowed in the early universe. And here, in the spiderweb, they're still visible, not yet erased by billions of years of cosmic evolution. It's a reminder that even the mightiest structures in the universe began as faint ripples in the fabric of space. So what does this mean for our understanding of the cosmos? The Spiderweb Galaxy isn't just a relic. It's a Rosetta Stone, helping us decode how the universe grew from a smooth, hot soup after the Big Bang into the intricate web we see today. Every collision, every stream of gas, every newborn star in this chaotic nursery is a piece of the puzzle. And as we study it, we're not just looking back in time, we're uncovering the blueprints for everything that came after, including our own place in the cosmic tapestry. If the Spiderweb Galaxy showed us the chaotic birth of cosmic structures, then the Coma Cluster is its grand culmination, a sprawling metropolis of over 1,000 galaxies, all bound together in a gravitational embrace so powerful it warps the very fabric of space around it. Located about 320 million light-years away in the constellation Coma Berenices, this isn't just another galaxy cluster. It's a laboratory for understanding how dark matter sculpts the universe on the largest scales. Picture a cosmic city where galaxies take the place of buildings, hurtling past one another at millions of miles per hour, their paths dictated by invisible hands. What makes the Coma Cluster so special isn't just its sheer size, it's the way it reveals dark matter's hidden architecture. While we can't see dark matter directly, its presence is betrayed by the cluster's gravitational grip, which is so strong it bends light itself. This phenomenon, called gravitational lensing, turns the cluster into a natural telescope. Distant galaxies behind Coma appear stretched and distorted, their light curving around the cluster like water flowing around a stone. By mapping these distortions, astronomers have reconstructed the cluster's dark matter skeleton, an invisible framework that holds this galactic megacity together. It's like seeing the shadow of something vast and unseen, its outline traced by the way it bends the light around it. But the Coma Cluster isn't just a static showcase, it's a dynamic, violent place. At its heart lies a pair of supergiant elliptical galaxies, NGC 4889 and NGC 4874, each over 10 times the mass of our Milky Way. These titans didn't grow so large by accident. They've spent billions of years cannibalizing smaller neighbors, growing fat on a diet of stars and gas. Surrounding them are thousands of other galaxies, some spirals rich with star-forming gas, others red and dead ellipticals whose fuel was stripped away long ago. The cluster's core is so densely packed that galaxies frequently collide, though the vast distances between stars mean these encounters rarely result in stellar smash-ups. Instead, galaxies pass through one another like ghosts, their gas torn away by the encounter and left behind in glowing streamers. Yet the real drama happens in the space between galaxies. The cluster is filled with superheated gas, reaching temperatures of tens of millions of degrees, so hot it emits X-rays. This gas isn't just a byproduct, it's a fossil record of the cluster's history. As galaxies move through it, they leave wakes like ships plowing through water, their motion stirring the intergalactic medium. Some galaxies have been completely stripped of their gas, left as barren husks adrift in this cosmic sea. Others, like the infamously headless galaxy IC4051, have had their star-forming material ripped away, leaving behind a trail of orphaned stars. A galactic crime scene where dark matter's pull is the prime suspect. The Coma Cluster's most astonishing feature might be its sheer gravitational reach. Beyond its visible galaxies lies an enormous halo of dark matter, stretching millions of light years further than the cluster's luminous core. This halo isn't just a backdrop, it's actively shaping the future of everything within its grasp. Astronomers have discovered galaxies being pulled into the cluster from unimaginable distances, caught in a flow of matter so vast it defies comprehension. Some call it the Coma Supercluster, a structure so massive it influences the motion of galaxies across hundreds of millions of light years. What does this mean for our place in the universe? The Coma Cluster is a stark reminder that we're not just observers of the cosmic web, we're part of its grand current. Our own local group of galaxies may one day merge with the neighboring Virgo cluster, beginning a journey toward becoming something like Coma, a fate that awaits most galaxies in the universe. But beyond its apocalyptic beauty, Coma offers something even more precious, proof that the universe's hidden structure, woven from dark matter's invisible threads, is just as real as the stars we see. Every distorted galaxy, every X-ray glow, every stream of stolen gas is a clue to the forces that built the cosmos, and the forces that will one day tear it apart. The Boötes cluster isn't just another cosmic collision, it's a smoking gun in one of astronomy's greatest mysteries. When these two galaxy clusters plowed through each other hundreds of millions of years ago, they didn't just create a spectacular light show. They left behind forensic evidence that changed our understanding of the universe forever. What makes this system so groundbreaking isn't the galaxies themselves, but what happened to the stuff we can't see. Here, for the first time, we caught dark matter red-handed, revealing its ghostly presence in a way no telescope could ignore. Picture the scene: two massive clusters, each containing hundreds of galaxies, slamming together at speeds over 20 million miles per hour. The visible gas between galaxies, superheated to millions of degrees, should have been the star of the show. But when astronomers combined X-ray observations with gravitational lensing maps, something bizarre emerged. The hot gas, the only matter we expected to detect, had been slowed dramatically by the collision, like two clouds of smoke merging. Yet the cluster's gravity, traced by the way they bent light from background galaxies, didn't follow the gas at all. Instead, it raced ahead, as if most of the mass had simply passed through the collision untouched. This was the moment dark matter stopped being a theoretical necessity and became something tangible. The Boötes cluster proved dark matter doesn't interact like normal matter. It doesn't collide, slow down, or emit light. It's like watching two crowds of people walk through each other in perfect silence, their shadows continuing forward while their bodies get tangled. For scientists, this was the closest thing to seeing dark matter we've ever achieved. The implications were staggering. If most of the universe's mass is invisible and intangible, then everything we see, stars, galaxies, even our own bodies, is just the faintest shimmer on an ocean of something far stranger. What's even more fascinating is how this collision mirrors the universe's largest scale behavior. The Boötes cluster isn't just a curiosity, it's a scaled-down version of how the cosmic web evolved. Dark matter's tendency to stream past collisions allowed it to form the universe's scaffolding first, creating gravitational wells where normal matter could later gather. Without this invisible framework, galaxies might never have clumped together, and the cosmic web as we know it wouldn't exist. The Boötes cluster shows us this process frozen in time, a snapshot of dark matter doing the heavy lifting while visible matter trails behind. Yet this discovery didn't just answer questions, it sparked new ones. Why does dark matter ignore normal matter so completely? Could it interact with itself in ways we haven't detected? Some theories even suggest the Boötes cluster might hide clues about dark matter's ultimate nature, whether it's made of undiscovered particles, primordial black holes, or something even more exotic. Every new observation peels back another layer, bringing us closer to understanding the force that shaped the cosmos. The Boötes cluster's legacy extends far beyond a single collision. It taught us to stop looking for dark matter where we expect to find it, and instead follow the gravitational breadcrumbs it leaves behind. Today, astronomers use these same techniques to map dark matter across the entire universe, tracing filaments too faint to see and voids too empty to comprehend. It's a reminder that sometimes the most profound truths aren't written in the light of stars, but in the silent spaces between them. The Hubble Ultra Deep Field isn't just a photograph, it's a time machine, a keyhole through which we peer into the universe's deepest secrets. Imagine pointing the most powerful telescope ever built at what appears to be an empty patch of sky, no bigger than a grain of sand held at arm's length. Then, after hundreds of hours of exposure, that tiny speck blossoms into a mosaic of over 10,000 galaxies, each a swirling island of stars, dust, and possibilities. This isn't just an image, it's a revelation showing us that the cosmos is far more crowded, far more intricate than we ever dared to dream. What makes this glimpse so extraordinary isn't just the sheer number of galaxies, it's their variety. The ultra-deep field captures everything from majestic spirals to blazing starbursts, from ancient red giants to infant galaxies still taking their first cosmic breaths. Some of these galaxies are so distant their light has traveled for over 13 billion years to reach us, meaning we're seeing them as they were when the universe was barely 5% of its current age. It's like flipping through a family album where each page shows a different stage of cosmic evolution, from toddlerhood to adolescence. And just like a family tree, these galaxies aren't isolated, they're connected, bound by the same invisible threads of gravity that weave the entire cosmic web. Zoom in on any corner of this image, and you'll notice something astonishing. The galaxies aren't scattered randomly. They cluster along faint filaments, tracing the same large-scale structure we see in the nearby universe, just on a younger, more chaotic scale. This is the cosmic web in its infancy, a blueprint of the universe's architecture still under construction. Some galaxies appear stretched or warped, their light bent by the gravitational pull of unseen dark matter. Proof that even in these early epochs, the invisible scaffolding of the universe was already shaping its destiny. Yet the true magic of the ultra-deep field lies in what it represents. That tiny patch of sky was chosen precisely because it seemed empty, a blank region where foreground stars wouldn't block our view. But the lesson it taught us was profound. There are no empty places in the universe. Every direction we look, no matter how void it appears, is teeming with galaxies. If the entire sky were this densely packed, the observable universe would contain over 100 billion galaxies, each with billions of stars of their own. It's a numbers game so vast it borders on the philosophical, how small we are, yet how connected to something unimaginably grand. This image also holds clues to one of astronomy's biggest puzzles. How did the cosmic web emerge from the formless fog of the early universe? By studying the ultra-deep field's faintest, most distant galaxies, astronomers have found they're not evenly distributed, they're already clustering, pulled together by gravity's whisper in the darkness. These fledgling structures would grow over billions of years, merging and colliding to form the vast filaments and voids we see today. In a very real sense, this snapshot captures the universe learning how to build itself. The Hubble Ultra Deep Field isn't just a scientific tool, it's a mirror, reflecting back our own curiosity and wonder. It reminds us that exploration isn't just about traveling outward, but backward through time, unraveling the story written in starlight. And as we prepare for even deeper observations with the James Webb Space Telescope, one thing is certain: the universe still has countless stories left to tell, hidden in the darkness between the stars. While we often marvel at the universe's grandest structures, its colossal walls and dazzling galaxy clusters, some of the most profound mysteries lie in what's missing. Enter the local void, a vast cosmic emptiness stretching over 150 million light-years, lurking just beyond our Milky Way's doorstep. This isn't just an empty patch of space, it's a gravitational anomaly, a void so devoid of matter that it actively repels galaxies, including our own. Picture a cosmic game of tug-of-war, where the Milky Way isn't just being pulled toward dense regions like the Great Attractor, it's also being pushed by this immense nothingness. The local void's influence is subtle but undeniable. Unlike the crowded neighborhoods of galaxy clusters, where gravity herds stars together like sheep, this region is so empty that its gravitational pull is practically non-existent. But here's the twist: in the cosmic web, emptiness isn't passive. The lack of mass here means galaxies on the void's edges experience an imbalance. They're drawn more strongly toward denser regions elsewhere, creating the illusion that the void itself is pushing them away. It's like standing in a room where one wall suddenly vanishes. You'd naturally drift toward the remaining walls, not because something pushed you, but because nothing's holding you back. This peculiar dynamic has left its mark on our galactic neighborhood. Observations show that the Milky Way, along with our neighboring Andromeda Galaxy and dozens of smaller companions, are all moving away from the local void at over 600,000 miles per hour. That's not just random drift, it's a direct response to the void's gravitational deficit. Even more intriguing, this motion isn't perfectly aligned with the pull of the Great Attractor, suggesting the local void is a silent partner in shaping our cosmic trajectory, its absence as influential as any visible force. Yet the local void isn't entirely empty. Scattered across its expanse are a handful of isolated galaxies, like lone travelers crossing a desert. These galaxies, often small and faint, are some of the most metal-poor ever observed, a clue that they've been cut off from the cosmic mainstream for billions of years, starved of the gas and dust that fuels star formation in denser regions. Studying them is like finding fossils in a wasteland. Their unusual properties hint at how extreme environments shape galactic evolution. Some even appear stretched, their stars pulled into streamers by the void's gravitational tides, as if space itself is slowly unraveling them. What makes the local void truly remarkable is how it challenges our perception of nothingness. Far from being inert, this void is an active player in the cosmic web, its emptiness sculpting the flow of galaxies as surely as any cluster or filament. And it's not alone. Recent surveys suggest our universe might be filled with similar voids, each contributing to the grand gravitational dance in ways we're only beginning to understand. The local void reminds us that in the cosmos, even nothing is something, a force that shapes, pushes, and ultimately helps weave the universe into the tapestry we see today. The Sloan Digital Sky Survey didn't just map the universe, it revealed its hidden skeleton. For centuries, astronomers saw galaxies as isolated islands adrift in the void. But this ambitious project peeled back the curtain to show something far more intricate, a delicate lacework of filaments stretching between galaxy clusters like celestial bridges. These aren't just decorative flourishes, they're the cosmic web's vital arteries funneling gas, dust, and entire galaxies across unimaginable distances over billions of years. What makes these filaments so extraordinary is how they shape the universe's growth. Picture them as cosmic highways, but instead of cars, they guide the flow of matter itself. When the survey first unveiled their structure in the early 2000s, it was like seeing the blueprint of a city for the first time. Suddenly, the seemingly random distribution of galaxies made sense. They were clustered along these threads like beads on a string, drawn together by gravity's invisible hand. The filaments themselves are woven from dark matter, that mysterious substance that makes up over 80% of the universe's mass. Like scaffolding at a construction site, these dark matter strands formed first, creating channels where ordinary matter could later gather and condense into galaxies. But the real magic happens in the gas these filaments transport. Observations show they're filled with diffuse, superheated plasma, the raw material for future stars and galaxies. This isn't just any gas, it's the universe's primordial fuel, left over from the Big Bang itself. As it streams along the filaments, it piles up at intersections where filaments meet, creating dense knots that eventually collapse into galaxy clusters. It's a cosmic delivery system, one that's been running non-stop for over 13 billion years. Some of this gas is still falling into clusters today, sparking bursts of star formation so intense they outshine entire galaxies. The scale of these structures defies earthly comparison. A single filament can stretch hundreds of millions of light years, yet be only a few million light years wide, razor thin on cosmic scales. They're so tenuous that until the Sloan survey, we had no way to detect them directly. Instead, astronomers traced their outlines indirectly, using the precise positions of millions of galaxies to reconstruct the web between them. It's like mapping a forest by noting where trees are densest, then inferring the root network beneath. Perhaps most astonishing is how these filaments solve a long-standing cosmic mystery. How did the universe go from a smooth, nearly uniform soup after the Big Bang to the clumpy, structured cosmos we see today? The answer lies in the subtle gravitational tugs of dark matter, which amplified tiny density fluctuations in the early universe, sculpting them into this vast network. The filaments we see now are the end result of that process, the universe's way of organizing chaos into order. Yet for all we've learned, these cosmic threads still hold secrets. Some appear too thin to survive the violent motions of galaxies, yet they persist. Others seem to glow faintly with the light of ionized gas, a phenomenon we're only beginning to understand. And then there's the question of what happens when filaments collide. Do they merge like streams or snap like overstretched wires? Each new survey peels back another layer, revealing a universe more interconnected, more dynamic than we ever imagined. The Sloan survey's greatest gift wasn't just a map, it was a paradigm shift. By revealing these filaments, it showed us that galaxies aren't solitary wanderers, but nodes in a grand network, each connected to the whole by threads of dark matter and destiny. And as we continue to chart this web, we're not just exploring space, we're tracing the very fabric of cosmic history. In the grand atlas of cosmic structures, few discoveries have rewritten the map as dramatically as the Boötes Great Wall. Found in 2016 by the Borean Oscillation Spectroscopic Survey, this titanic filament stretches over 1 billion light years, a galactic superhighway paved with thousands of galaxies, each a city of stars in its own right. But what makes this wall truly groundbreaking isn't just its jaw-dropping scale, it's how we found it. Unlike traditional surveys that rely on light alone, Boötes used a far more subtle tool, echoes from the universe's infancy, frozen in time as ripples through space itself. These echoes, known as Baryon acoustic oscillations, are the universe's original sound waves. Picture the early cosmos as a vast, hot soup of particles where pressure waves, like sound rippling through water, propagated outward from every density fluctuation. When the universe cooled enough for atoms to form, these waves froze in place, imprinting a preferred distance between galaxy clusters that persists to this day. By measuring this cosmic ruler, about 500 million light-years long Boötes could map the Boötes Great Wall with unprecedented precision, revealing not just where galaxies are, but how the space between them was sculpted by primordial forces. What emerged was a structure so vast it challenges our understanding of cosmic evolution. The wall's galaxies aren't just clustered, they're aligned along filaments so precise they resemble the grooves in a fingerprint. Some researchers speculate this level of organization couldn't have arisen from random fluctuations alone. It might hint at unknown physics in the early universe, or even relics from an era before the Big Bang. Others suggest the wall could be a superhighway for dark matter, its gravitational currents funneling galaxies into these staggering alignments over billions of years. Yet the Boötes Great Wall's greatest surprise lies in its emptiness. Like all cosmic filaments, it's not solid. Its galaxies are separated by voids so vast they'd swallow our local group without a trace. These voids aren't just gaps, they're active participants in the wall's dynamics, their lack of gravity allowing the surrounding galaxies to flow along the filaments like water through a canyon. Modern simulations show this interplay between dense threads and empty spaces is what gives the cosmic web its strength, with voids acting as cosmic repellers that herd galaxies into ever tighter formations. What does this mean for our place in the universe? The Boötes Great Wall is more than a distant curiosity. It's a mirror reflecting the forces that shaped our own galactic neighborhood. The same oscillations that built this colossus also nudged the Milky Way into existence, linking us to structures so distant their light hasn't reached us yet. And as future surveys map even larger volumes of space, who knows what other walls or deeper mysteries might emerge from the shadows. For now, the Boötes Great Wall stands as a testament to the universe's boundless talent for surprise, proving that even in its grandest designs, there are always new patterns waiting to be read. Our Milky Way isn't just a swirling disk of stars, it's cloaked in an invisible giant, a halo of dark matter so vast it stretches 10 times farther than the galaxy's visible edge. Picture a lighthouse surrounded by fog. The beam you see is the Milky Way's glowing spiral, but the true mass, the gravitational anchor holding everything together, is the unseen mist enveloping it. This dark matter halo isn't just a passive bystander, it's the reason our galaxy hasn't flown apart, the hidden hand guiding stars in their orbits and sculpting our cosmic destiny. What makes this halo so extraordinary is how little it resembles the galaxy we see. While the Milky Way stars are concentrated in a flat, spinning disk, the dark matter forms a spherical cloud, its density fading gently as it blends into the intergalactic void. We can't see it, touch it, or even detect it directly, yet its gravitational pull is unmistakable. Stars in the outer reaches of the galaxy rotate far faster than they should if only visible matter were tugging on them, like cars on a racetrack mysteriously speeding up with no apparent engine. The only explanation, an enormous, invisible mass dark matter wrapping the galaxy in its embrace. This hidden structure isn't just holding the Milky Way together, it's a time capsule from the galaxy's birth. Simulations suggest the halo formed first, a gravitational well so deep that ordinary matter, gas, dust, and eventually stars couldn't resist its pull. Over billions of years, this infalling material settled into the disk we recognize today, while the dark matter remained aloof, a silent partner in the Milky Way's evolution. Even now, it's not static. The halo pulses with streams of dark matter, remnants of smaller galaxies torn apart by our galaxy's gravity, their debris tracing ghostly rivers through the darkness. But the halo's influence extends far beyond our galactic borders. It's the reason the Milky Way and Andromeda are destined to collide in 4 billion years. Their dark matter halos already brushing against one another in the cosmic dark, drawing them inexorably closer. And it's not just Andromeda. Dwarf galaxies like the large and small Magellanic clouds orbit the Milky Way only because the halo's gravity holds them captive. Without it, these satellite galaxies would have drifted away eons ago, lost to the void. Yet for all its power, the Milky Way's halo is just one thread in a larger tapestry. It connects to filaments of dark matter that stretch across the local universe, tying our galaxy to the cosmic web. Recent studies suggest these filaments might funnel dark matter into the halo like underground aquifers feeding a spring, a process that could explain why the halo's outer edges appear fluffier than predicted. Some theories even propose that dark matter isn't uniform. It might clump into invisible subhalos within the larger halo, like shadowy Russian nesting dolls hiding in plain sight. The search to understand this enigmatic structure is far from over. Telescopes like Gaia map the motions of billions of stars, tracing the halo's gravitational fingerprints. Particle detectors buried deep underground hunt for fleeting interactions between dark matter and ordinary atoms, and simulations grow ever more sophisticated, revealing how the halo might vibrate like a struck bell when smaller galaxies pass through it. Each clue brings us closer to answering the ultimate question: what is dark matter, and how did it sculpt the galaxy we call home? One thing's certain: the Milky Way's halo isn't just an artifact, it's an active player in the cosmic web. Its gravity shapes nearby galaxies, steers intergalactic gas, and may even determine our place in the universe's grand architecture. As we peer deeper into its mysteries, we're not just studying an invisible cloak, we're unraveling the very fabric of our galactic story. Nestled just 60 million light-years away, practically next door in cosmic terms, the Fornax cluster offers a front-row seat to the cosmic web's relentless dance. Unlike distant megastructures, Fornax is close enough for telescopes to capture its galaxies in stunning detail, each one a snapshot of how dense environments shape galactic fate. Picture a crowded metropolis where skyscrapers are galaxies, their gravity tugging at neighbors, stealing gas, and rewriting destinies with every close encounter. This isn't just a cluster, it's a laboratory for understanding how the universe's largest structures sculpt the galaxies within them. At its heart lies NGC 1399, a monstrous elliptical galaxy that dominates the cluster like a gravitational monarch. Ellipticals like this are the end result of cosmic cannibalism: galaxies that have gorged on neighbors until their once spiraled arms blurred into a featureless glow. Surrounding it are hundreds of smaller galaxies, some spirals rich with star-forming gas, others red and dead ellipticals whose fuel was stripped away long ago. The cluster's core is so densely packed that galaxies frequently collide, though stars themselves rarely crash instead. Their gas is ripped away in spectacular tidal tails, igniting bursts of new stars or vanishing into the intergalactic void. What makes Fornax special isn't just the violence, it's the subtle clues it offers about the cosmic web's influence. Between its galaxies stretches a sea of superheated gas, detectable only in X-rays. This gas isn't static. It's a dynamic medium that galaxies swim through, their motion leaving wakes like ships plowing through water. As galaxies move, they lose their own gas to this intracluster medium, a process called ram pressure stripping. The result, spiral galaxies transformed into gas-starved ellipticals, their star-forming fuel stolen by the cluster itself. It's a stark reminder that in the cosmic web, even emptiness has teeth. Yet Fornax also harbors mysteries. One of its most famous residents, the spiral galaxy NGC 1365, shouldn't exist here. Spirals are fragile, their delicate arms easily disrupted by cluster encounters, yet NGC 1365 has survived, its star-forming arms intact. Astronomers suspect it's a recent arrival, still on its first plunge through the cluster's outskirts. By studying such survivors, we're learning how galaxies navigate the cosmic web's dense knots and why some emerge unscathed while others are torn apart. The cluster's dark matter halo adds another layer of intrigue. Like all galaxy clusters, Fornax is swathed in an invisible cocoon of dark matter, its gravity bending light from background galaxies into faint arcs, a phenomenon called weak gravitational lensing. By mapping these distortions, astronomers have reconstructed the halo's shape, revealing it's not perfectly spherical but stretched, likely by interactions with nearby clusters. This distortion hints at a larger truth. Fornax isn't an island. It's linked by dark matter filaments to the wider cosmic web, part of a vast network we're only beginning to trace. Perhaps Fornax's greatest gift is its humanity. Unlike distant clusters frozen in time, Fornax is close enough to watch changes unfold on astronomical timescales. Here we've caught galaxies in the act of merging, their gas streaming into space. We've seen dwarf galaxies being torn apart, their stars scattered into faint streams. And we've witnessed the quiet deaths of spiral arms, their gas stripped away by the cluster's relentless grip. Each event is a chapter in the story of how the cosmic web shapes galaxies, a story that, thanks to Fornax, we're finally learning to read. Somewhere in the darkness beyond the Milky Way's glittering disk, an invisible force is rewriting the destiny of our galaxy and thousands of others. This is the Great Attractor, a gravitational anomaly so powerful it bends the paths of entire galaxies toward it like rivers flowing toward a hidden sea. Lurking behind the Milky Way's central bulge, a region so dense with stars and dust we call it the zone of avoidance. This enigmatic presence tugs at us with the force of 100 quadrillion suns, yet remains almost entirely hidden from view. It's as if the universe built a curtain across the cosmos's greatest stage, and we're only just beginning to peek behind it. For decades, astronomers puzzled over why our local group of galaxies, along with countless others, races through space at over 1 million miles per hour toward the constellations Centaurus and Hydra. The first clues emerged in the 1970s when measurements revealed this motion couldn't be explained by visible matter alone. Something colossal, something unseen, was pulling us toward it. The Great Attractor wasn't just a mystery, it was a revolution proving that the universe's largest structures could hide in plain sight. Their gravity felt long before their forms were known. Peering through the zone of avoidance required more than optical telescopes. It demanded ingenuity. Infrared surveys like the 2-micron all-sky survey pierced the dust, revealing a crowded realm of galaxies previously obscured. At the heart of this hidden realm lies the Coma Cluster, a massive gathering of galaxies that accounts for some but not all of the attractor's pull. Beyond it, something even larger looms, the Shapley Supercluster, a staggering concentration of matter over 650 million light-years away, whose gravity may contribute to the Great Attractor's influence. Together, these structures form a cosmic watershed, where galaxies flow like streams toward a gravitational basin we're still mapping. But here's where the plot thickens. Even adding up all the visible mass in these clusters falls short of explaining the attractor's full strength. The rest, scientists suspect, lies in dark matter, the invisible scaffolding that shapes the cosmic web. The Great Attractor might not be a single object, but a confluence of dark matter filaments, a knot in the universe's hidden lattice where gravity's threads converge. Picture a whirlpool in an ocean current, drawing everything toward its center, except this whirlpool is woven from the fabric of space itself. What makes this cosmic mystery so tantalizing is its intimacy. We're not just observers of the Great Attractor's pull, we're participants, caught in its flow. In about 5 billion years, the Milky Way's merger with Andromeda may send our combined galaxy hurtling even faster toward this gravitational beacon, a journey that will continue long after our sun has faded. The attractor reminds us that we're not just floating in space, we're sailing on unseen tides, pulled by forces that have shaped the universe since its birth. Yet for all we've learned, the Great Attractor guards its secrets fiercely. Is it truly a distinct structure, or just a waypoint on a larger current? Could its apparent pull be the echo of something even more colossal beyond our observable horizon? Each new survey peels back another layer of the zone of avoidance, but the universe, it seems, always keeps one more card up its sleeve. One thing's certain, as we unravel this gravitational riddle, we're not just solving a cosmic mystery, we're learning to read the invisible handwriting of the universe itself. The Virgo Supercluster isn't just another entry in the cosmic atlas, it's our galactic neighborhood's grandest scale, a sprawling metropolis of galaxies that includes the Milky Way and about 100 other galactic groups. Picture a celestial city where each borough is a cluster or group of galaxies, and the streets are the dark matter filaments connecting them, spanning over 110 million light-years. This supercluster is anchored by the Virgo cluster at its heart, a dense gathering of over 1,000 galaxies whose gravity orchestrates the motion of everything around it, including our own local group. What makes the Virgo supercluster so fascinating isn't just its size, it's how it reveals the universe's nested structure. Like Russian dolls, cosmic webs nest within one another, each layer a larger echo of the one before. Our Milky Way resides in the local group, which orbits within the Virgo supercluster, which itself is just one lobe of the even vaster Laniakea Supercluster. This fractal-like organization hints at a universal blueprint where gravity sculpts matter into patterns that repeat across scales, from the tiniest galactic mergers to the grandest supercluster flows. The supercluster's influence is everywhere. The Milky Way and Andromeda, along with their entourage of dwarf galaxies, are all slowly falling toward the Virgo cluster, drawn by its immense gravitational pull. This motion isn't a straight plunge, it's a cosmic dance, with galaxies threading along dark matter filaments like beads on a string, their paths curved by the interplay of countless invisible forces. Even our own galaxy's trajectory bears the supercluster's fingerprints, a reminder that no island in the cosmos is truly isolated. Yet the Virgo supercluster isn't static. It's a dynamic, evolving structure with galaxies constantly merging, clusters colliding, and gas streaming between them. The Virgo cluster itself is a prime example. Its central galaxy, M87, famously hosts a supermassive black hole whose jet stretches thousands of light-years into space, a testament to the violent processes shaping these dense regions. Meanwhile, smaller groups like our local group orbit the periphery, destined to one day merge into the cluster's core, billions of years in the future. This supercluster also offers a front-row seat to one of cosmology's biggest puzzles. How do galaxies transition from vibrant, gas-rich spirals to red and dead ellipticals? In the Virgo cluster's crowded core, Galaxies are stripped of their gas by relentless collisions and the superheated plasma between them, leaving behind ghostly shells of stars. By contrast, outlying galaxies like our own remain relatively unscathed for now. The Virgo Supercluster is a living laboratory, showcasing every stage of galactic life and death in one vast cosmic ecosystem. But perhaps its greatest lesson is one of perspective. The Virgo Supercluster reminds us that our Milky Way isn't just a solitary spiral. It's part of something far grander, a single thread in a web that stretches across the observable universe. And as we map these connections, we're not just charting space, we're tracing the gravitational bonds that have shaped our past and will dictate our future. Amid the crushing emptiness of the Boötes void, a cosmic desert spanning 330 million light-years, one lonely galaxy defies all expectations. MCG plus 01-02-015 floats in perfect isolation, the only beacon of starlight in an ocean of darkness so vast it could swallow our entire local group without a trace. This isn't just a galaxy surviving in harsh conditions. It's a cosmic castaway separated from its nearest galactic neighbor by millions of light-years of pure nothingness. How does a galaxy end up so utterly alone? The answer challenges everything we know about cosmic evolution. Most galaxies form along dense filaments of dark matter, where gravity gathers gas into swirling disks. But MCG plus 01-02-015 appears to have been born in the void itself, a cosmic miracle growing where there should be no material to fuel it. One theory suggests it might be the last survivor of a group of galaxies, its companions long since stripped away by the void's expansion. Another posits that it formed from a rare, isolated pocket of gas left behind when the cosmic web first took shape, like a single rain puddle lingering in a parched riverbed. The galaxy's isolation has left its mark. Unlike clustered galaxies, which often run out of star-forming gas due to violent collisions or theft by neighbors, this lone wanderer has held onto its reserves for billions of years. Observations reveal it's unusually rich in hydrogen gas, the raw material for new stars, and its star formation rate is higher than expected for a galaxy its size. It's as if the void, by denying it neighbors, also spared it the turmoil that typically disrupts galactic growth. Yet even here, in this quiet corner of the universe, the void exacts a price. Without the gentle gravitational nudges from nearby galaxies, MCG plus 01-02-015 has likely never experienced the majestic spiral arms or dramatic interactions that shape most galaxies. Its existence is one of serene, uninterrupted solitude. But the real mystery isn't just how this galaxy exists, it's what its existence tells us about voids themselves. Astronomers once thought these regions were completely barren, cosmic dead zones where nothing could form. Yet MCG plus 01-02-015 proves that even the emptiest places in the universe can, against all odds, spark with starlight. Its presence suggests voids might be more dynamic than we imagined, with hidden currents of gas or dark matter too faint for our telescopes to detect. Some simulations even hint that void galaxies could be fed by whisper-thin filaments, strands of the cosmic web so tenuous they're nearly invisible. This lonely galaxy also offers a glimpse into an alternate cosmic fate. Had our Milky Way formed in such isolation, our night sky would be unrecognizable, no Andromeda looming on the horizon, no Magellanic clouds to guide ancient navigators. Instead, the void around MCG plus 01-02-015 stretches so empty that if its inhabitants looked out, they'd see only darkness punctuated by the faint glow of distant superclusters. their light stretched thin by billions of years of travel through expanding space. Yet for all its strangeness, MCG plus 01-02-015 isn't entirely unique. A handful of other void galaxies have been discovered, each a solitary island in the cosmic dark. Together, they challenge our assumptions about where life might arise in the universe. Could planets orbiting stars in these isolated galaxies look up to skies devoid of neighboring galaxies, their civilizations unaware of the bustling galactic cities beyond? The Boötes Void's lone galaxy doesn't just defy expectations. It invites us to reimagine the diversity of cosmic habitats, proving that even in the emptiest reaches of space, the universe finds a way to shine. Beneath the grand tapestry of galaxies and dark matter filaments lies an even more elusive secret, the cosmic neutrino background. These ghostly particles, born just 1 second after the Big Bang, flood every cubic inch of the universe, passing through planets, stars, and even you right now at nearly the speed of light. Unlike the cosmic microwave background, the afterglow of the universe's birth that we can see, this neutrino sea is invisible, undetectable by ordinary telescopes. Yet these faint whispers from the dawn of time may hold the missing clues to how the cosmic web first emerged from the primordial chaos. Imagine the early universe as a seething ocean of energy, so dense that even neutrinos, particles that barely interact with matter, were trapped in the hot plasma. When the universe cooled enough to let them escape, they streamed outward in all directions, carrying with them a snapshot of the cosmos at that critical moment. That was over 13 billion years ago, and those same neutrinos still permeate space today, their patterns subtly imprinted with the seeds of future galaxies. The problem: neutrinos are the universe's ultimate ghosts. A trillion pass through your body every second without a trace, their signals drowned out by cosmic noise. But why chase such elusive prey? The answer lies in their unique role as cosmic sculptors. In the universe's first seconds, neutrinos made up a significant fraction of its mass, their sheer numbers giving them surprising gravitational influence. As they streamed outward, their slight density variations, echoes of quantum fluctuations from the Big Bang, helped tug matter into the first wispy filaments of the cosmic web. Unlike dark matter, which clumped together under gravity's pull, neutrinos moved too fast to stay in one place, smoothing out some regions while amplifying others. This delicate dance between fast-moving neutrinos and slow-gathering dark matter may have determined where galaxies eventually formed and where vast voids took shape. Detecting this background isn't just a technical challenge, it's a window into physics we can't recreate. Current experiments like Super Kamiok and in Japan, or the upcoming Deep Underground Neutrino experiment in the U.S. hunt for these relics by watching for the rare occasions when a cosmic neutrino bumps into an atomic nucleus. The telltale flash of light from such an event would be vanishingly faint, but if captured, it could reveal the neutrino's original energy and thus its age. By mapping their distribution, we might finally see the universe's skeleton as it looked before the first stars ignited, tracing how infinitesimal ripples grew into the vast web we observe today. The implications stretch beyond cosmology. If the neutrino background's patterns match predictions, it would confirm our models of the early universe with unprecedented precision. But if they don't, that discrepancy could point to unknown physics, perhaps evidence that neutrinos have unexpected properties, or that other exotic particles played a role in shaping the cosmos. Some theories even suggest neutrinos might interact with dark matter in ways we haven't imagined, their ghostly motions subtly guiding the invisible hands that built the universe. What makes this search so thrilling isn't just the potential discoveries, it's the sheer audacity of trying to capture shadows from the universe's first breath. While the cosmic microwave background shows us the universe at 380,000 years old, the neutrino background would take us back to its first second, a time when the cosmos was a seething forge of creation. And as detectors grow more sensitive, we edge closer to reading this ancient manuscript, written not in light or matter, but in the faintest tremors of particles that have witnessed everything. The cosmic web didn't just form in empty space, it was woven by these invisible threads, and their story, once deciphered, might rewrite our understanding of cosmic destiny itself. Among the most brilliant and baffling structures in the cosmos are the large quasar groups, colossal gatherings of quasars so vast they make galaxy clusters look like specks of dust. These titanic assemblies stretch across staggering distances, some spanning more than 4 billion light-years, with quasars aligned in patterns that defy our expectations of how the universe should look on such enormous scales. A single one of these groups can contain dozens of quasars, each the luminous core of a distant galaxy powered by a ravenous supermassive black hole. Together, they form the universe's largest and most luminous patterns, cosmic lighthouses shining across the void in formations that shouldn't exist. The discovery of these groups sent shockwaves through cosmology because they directly contradict one of astronomy's foundational ideas, the cosmological principle. This principle states that at sufficiently large scales, the universe should appear roughly uniform, with matter distributed evenly in all directions. But the large quasar groups are anything but uniform. Their quasars cluster together in intricate, interconnected chains, like beads on a string stretched across billions of light-years. Finding structures this enormous challenges our understanding of how the cosmos evolved, suggesting that either our models are incomplete or the universe is far stranger than we ever imagined. What makes quasars such critical markers is their sheer luminosity. Powered by supermassive black holes devouring surrounding matter, they outshine entire galaxies, making them visible across mind-bending distances. When astronomers map their positions, they're not just plotting points of light, they're tracing the underlying architecture of the universe itself. The quasars in these groups aren't randomly scattered. They follow the contours of the cosmic web, aligning along filaments of dark matter just like galaxies do. But here's the puzzle. The scales involved are so vast that, according to standard cosmological models, there hasn't been enough time since the Big Bang for gravity to pull matter into such enormous structures. So how did they form? One leading theory points to primordial density fluctuations, tiny ripples in the fabric of the early universe that were amplified over billions of years by gravity. In most regions, these fluctuations averaged out, creating the relatively even distribution of galaxies we see today. But in the case of large quasar groups, these ripples might have been unusually strong, creating dense regions where matter clumped together on scales we once thought impossible. Another, more radical idea suggests these structures could be evidence of exotic physics, perhaps even relics from a time before the Big Bang, imprinted on the cosmos in ways we don't yet understand. Yet the most tantalizing possibility is that these groups are signposts to something even larger. Some astronomers speculate they might be part of a hierarchy of structure we're only beginning to glimpse, nodes in a network so vast it extends beyond the observable universe. If true, the largest quasar groups could be the visible tips of cosmic icebergs, their full dimensions hidden by the limits of our telescopes. Future surveys, like those planned with the Vera Rubin Observatory and the James Webb Space Telescope, aim to map these structures in unprecedented detail, potentially revealing whether they're rare anomalies or fragments of a grander design we've yet to comprehend. What's certain is that these luminous giants force us to rethink the universe's blueprint. They remind us that even our most foundational assumptions must be tested against the cosmos's boundless creativity. And as we probe deeper into their mysteries, we're not just studying distant quasars, we're deciphering the universe's boldest strokes, written in light across the vast canvas of space and time. The Zwicky Cluster isn't just a gathering of galaxies, it's a cosmic funhouse mirror, warping the fabric of space-time so dramatically that light from distant objects bends around it like water flowing around a boulder. Officially known as Able 1656, this colossal assembly of over 400 galaxies sits roughly 2.3 billion light-years away, its immense gravity acting as a natural telescope that magnifies and distorts the universe behind it. But what makes this cluster truly extraordinary isn't just its sheer mass, it's how it reveals the invisible. Every twisted arc and duplicated galaxy in its wake is a clue to dark matter's hidden architecture, a ghostly blueprint we're only beginning to decode. When light from a distant galaxy passes near the Zwicky Cluster, it doesn't travel in a straight line, it follows the curves of warped space-time, creating surreal optical illusions called Einstein rings or multiple images of the same object. Imagine holding a magnifying glass over a crumpled sheet of paper. The lens doesn't just enlarge the text, it stretches and fractures it into strange new shapes. That's exactly what happens here, except the lens is the combined gravity of hundreds of galaxies and their surrounding dark matter halos, and the text is the light from galaxies far beyond. These distorted images aren't just cosmic curiosities, they're precise measurements of gravity's grip, allowing astronomers to weigh the cluster and map its unseen dark matter with unprecedented precision. What's astonishing is how much of this cluster's mass remains invisible. Visible galaxies account for less than 5% of its total gravitational pull. The rest is dark matter, an enigmatic substance that neither emits nor reflects light. By analyzing how the cluster bends background light, scientists can trace dark matter's distribution like detectives dusting for fingerprints. The resulting maps reveal a sprawling, intricate web, with dark matter concentrated not just around the cluster's galaxies, but also forming vast bridges between them. These filaments are the cosmic web's backbone, the scaffolding upon which galaxies are built, and the Zwicky Cluster offers one of the clearest views of their structure. But the cluster's lensing effects do more than reveal dark matter. They also let us peer further into the universe's past than traditional telescopes allow. Some of the lensed galaxies behind Zwicky are so distant their light has traveled for over 10 billion years to reach us. Without the cluster's magnifying effect, these faint objects would be invisible to even our most powerful observatories. It's like stumbling upon a natural telescope built into the cosmos itself, one that lets us study the earliest epochs of galaxy formation in stunning detail. The Zwicky Cluster isn't a static relic, it's a dynamic collision in progress. Observations show it's actually two smaller clusters merging, their galaxies and dark matter halos smashing together at millions of miles per hour. This violence creates shock waves in the superheated gas between galaxies, visible in X-rays, while the dark matter, true to its elusive nature, passes through the chaos unaffected. This stark contrast between how normal and dark matter behave during collisions is one of the strongest pieces of evidence we have for dark matter's existence. The cluster is, in effect, a giant physics experiment, testing our theories on a scale no lab could ever replicate. What does this mean for our understanding of the cosmos? The Zwicky Cluster is more than a gravitational lens. It's a Rosetta Stone for deciphering the universe's hidden language. Every distorted image, every X-ray flare, every traced filament brings us closer to answering fundamental questions. How is dark matter distributed? How do clusters evolve? And what role do these colossal structures play in shaping the cosmic web? As new telescopes like Euclid and the Vera Rubin Observatory come online, they'll turn thousands more galaxy clusters into similar lenses, weaving a tapestry of dark matter maps across the entire sky. The Zwicky Cluster is just the beginning, a single thread in a story that will ultimately reveal the universe's deepest secrets. Stretching like a celestial river across the southern sky, the Magellanic Stream is a hauntingly beautiful scar left by the Milky Way's gravitational dominance, a ribbon of gas so vast it spans nearly half the visible universe from our vantage point. This shimmering filament, barely visible to the naked eye but glowing brightly in radio telescopes, tells the story of two small galaxies caught in an endless cosmic dance with our own. The large and small Magellanic Clouds, those familiar smudges of light orbiting the Milky Way, aren't just passive companions. They're being unraveled by the tidal forces of our galaxy, their gas stripped away over billions of years to form this ethereal trail. What makes the Magellanic Stream so remarkable isn't just its scale, it's the intimate window it provides into how galaxies grow and interact. Unlike the colossal walls and voids we've explored, this structure is a local phenomenon, a thread in the cosmic web woven right in our backyard. The gas composing it wasn't always adrift. It once belonged to the Magellanic Clouds, rich with the raw materials for new stars. But as these dwarf galaxies swung past the Milky Way, our galaxy's gravity acted like a colossal sieve, siphoning away their outermost layers. Picture two ships passing too close to a whirlpool, their cargo spilling into the current, except here, the ships are galaxies, and the cargo is the very stuff of star formation. The stream's existence challenges earlier assumptions about galaxy evolution. Astronomers once thought dwarf galaxies were too small to contribute meaningfully to larger ones. Yet here, stretched across 300,000 light-years, is proof that even the cosmos's smallest players shape their surroundings. The gas in this filament isn't just drifting, it's gradually falling toward the Milky Way, where it will one day fuel new generations of stars. In a very real sense, our galaxy is cannibalizing its neighbors, not by devouring them whole, but by sipping their essence over cosmic time. Yet the stream holds puzzles of its own. Its shape is more complex than a simple tidal tale, with twists and bifurcations that suggest a turbulent history. Some sections even seem to be moving backward, as if caught in an unseen eddy. The leading explanation: the Magellanic Clouds aren't just orbiting the Milky Way, they're orbiting each other, their mutual gravitational tug-of-war adding kinks to the stream like knots in a rope. Computer simulations reveal this dance might be relatively recent. The clouds may have been independent wanderers until a close encounter a few billion years ago bound them to our galaxy. But the stream's most tantalizing secret is hidden in its composition. Spectroscopic studies show it contains less heavy elements, what astronomers call metals, than expected. This suggests much of its gas wasn't stripped from the cloud star-forming regions, but from their pristine outer halos, material untouched by stellar furnaces since the dawn of time. If so, the stream is more than a galactic casualty, it's a fossil, preserving the early universe's original chemistry in a way no telescope could observe directly. What does this mean for the cosmic web? The Magellanic Stream is a microcosm of the processes shaping the universe's largest structures. Just as dark matter filaments channel galaxies together, the stream guides gas toward the Milky Way, proving that the cosmic web operates on all scales. And it's not alone. Similar streams lace nearby galaxies like Andromeda, evidence that this slow-motion unraveling is universal. Far from being static, the cosmos is a dynamic tapestry, its threads continually rewoven by gravity's relentless hand. The stream's fate is written in the stars. In a few billion years, its gas will merge with the Milky Way's halo, potentially triggering a burst of star formation. By then, the Magellanic clouds themselves may be reduced to shreds, their remaining stars scattered into our galaxy's outer reaches. But their legacy will endure, not just in the stream, but in the generations of stars born from its sacrifice. It's a reminder that even the smallest threads contribute to the universe's grand design. Before the cosmic web shimmered with galaxies, before superclusters and vast voids took shape, the universe was a silent, lightless expanse, a sea of darkness stretching in every direction. This was the cosmic dawn, the moment when the first stars flickered to life, igniting the cosmos with their newborn glow. Picture a realm so alien it defies imagination. No planets, no galaxies, just an endless fog of hydrogen and helium, the sparse remnants of the Big Bang's fiery birth. Then, almost imperceptibly, gravity began to weave its magic. Tiny fluctuations in density, echoes of quantum, ripples from the universe's first moments grew stronger, pulling matter into delicate filaments. These were the cosmic web's first threads, invisible scaffolds upon which everything would later be built. The birth of those first stars wasn't just a milestone, it was a revolution. Unlike the stars we see today, these pioneers were colossal behemoths, hundreds of times more massive than our sun and blazing with fierce blue light. They lived fast and died young, their brief, brilliant lives ending in cataclysmic explosions that seeded the cosmos with heavier elements: carbon, oxygen, iron, the building blocks of planets and eventually life. But their greatest legacy wasn't the material they created, it was the light they cast. For the first time, photons pierced the primordial fog, a process called reionization, tearing apart hydrogen atoms and transforming the universe from opaque to transparent. This was the moment the cosmic dark truly ended, and the stage was set for galaxies to form. How do we study an era so remote, so faint that its light has been stretched by the expansion of the universe into microwave whispers? The answer lies in some of the most delicate observations ever made. Telescopes like the James Webb Space Telescope peer back in time, capturing infrared light from galaxies so distant we see them as they were just a few 100 million years after the Big Bang. These fledgling galaxies aren't the majestic spirals we know today. They're small, chaotic clumps of stars, often strung along filaments of dark matter like pearls on a string. Their distribution isn't random, it mirrors the cosmic web's infancy, revealing how gravity's invisible hand guided their growth. But the cosmic dawn wasn't a uniform sunrise. Some regions of the universe lit up earlier than others, creating a patchwork of light and shadow. Astronomers call this the epoch of reionization, and its uneven progress holds clues to how the cosmic web's large-scale structure emerged. Dense knots of matter, where dark matter filaments intersected, became the first stellar nurseries, their intense radiation bubbles expanding outward like cosmic wildfires. Between them, vast deserts of gas remained dark, destined to become the voids we see today. This interplay between illumination and emptiness set the template for everything that followed. The web's voids, walls, and clusters all trace their origins to this primordial dawn. One of the most astonishing revelations from this era is how quickly complexity arose. Simulations suggest the first galaxies may have formed astonishingly early, some perhaps just 200 million years after the Big Bang. These weren't the isolated islands we might expect. Instead, they were often part of sprawling networks, drawn together by the same dark matter filaments that would later bind superclusters. The cosmic dawn wasn't a slow awakening, it was a sudden, explosive blossoming of structure, as if the universe couldn't wait to weave its grand design. Yet for all we've learned, the cosmic dawn remains shrouded in mystery. Did the first stars form alone or in clusters? How did their violent deaths alter their surroundings? And perhaps most intriguingly, could their light carry traces of even earlier phenomena, like primordial black holes or exotic particles we've yet to discover? Each new observation peels back another layer, revealing a universe more dynamic, more inventive than we ever imagined. The cosmic dawn isn't just a chapter in cosmic history, it's the foundation of everything we see today, a reminder that even the grandest structures began as whispers in the dark. The cosmic web we see today, a glittering tapestry of galaxies strung along vast filaments, isn't eternal. Like all things in the universe, it has an expiration date. As the relentless expansion of space accelerates, driven by the mysterious force we call dark energy, the web's delicate threads will stretch and fray. Galaxies bound together today by gravity's invisible cords will one day find themselves drifting apart, their connections severed by the expanding void between them. What remains will be a cosmos unrecognizable from the vibrant network we observe, now a future where the universe's grand design unravels into darkness. Picture the cosmic web as a city at night, its streets illuminated by the glow of countless galaxies. Over the next 100 billion years, those lights won't just fade, they'll vanish, one by one, as the space between them grows too vast for their light to bridge. Galaxy clusters, those dense urban cores of the cosmos, will become isolated islands, their gravity no longer strong enough to hold back the tide of expansion. The filaments connecting them, once bustling highways of gas and galaxies, will thin into ghostly strands, their matter pulled apart like cotton candy stretched to breaking point. Even the closest neighbors will drift beyond each other's horizons, their light no longer able to reach one another across the expanding gulf. This slow dissolution isn't just theoretical, it's already underway. Dark energy's grip on the cosmos grows stronger with time, its repulsive force overpowering gravity's pull on the largest scales. In the far future, the universe will reach a point where no new structures can form. The raw materials for galaxies, the gas and dust flowing along filaments, will be spread so thin that star formation grinds to a halt. The last generation of stars will flicker out, leaving behind stellar corpses, white dwarfs, neutron stars, and black holes. Eventually, even these remnants will decay, their particles scattered across an ever-cooling cosmos. Yet the most haunting consequence of this expansion isn't the darkness, it's the isolation. Civilizations born in the distant future will look up to a night sky devoid of galaxies. Their telescopes, no matter how powerful, will reveal only the dim glow of their own cluster, the rest of the universe hidden behind an impenetrable curtain of expanding space. They'll have no way of knowing the universe was ever anything more than a lonely island of stars, adrift in an infinite void. The cosmic web's grandeur, its intricate connections, will be lost to time. But this bleak future isn't the only possibility. Some theories suggest dark energy's influence might change, perhaps weakening or even reversing, allowing gravity to regain control. Others propose more exotic fates, like the collapse of the universe in a big crunch or its rebirth in a cyclical cosmos. For now, these ideas remain speculative, their truth hidden in the same distant future they attempt to describe. The cosmic web's fate is a reminder of our extraordinary luck. We live in a golden age of cosmology, a brief window when the universe is old enough to have built complex structures, yet young enough that we can still see them. The same expansion that will one day tear the web apart has, for now, left it intact and visible, a masterpiece we're privileged to witness. As we map its filaments and trace its history, we're not just studying the universe, we're preserving its story, ensuring that even in the trillions of years to come, the memory of its grand design endures. From the largest walls spanning billions of light years to the faintest tendrils of dark matter, the cosmic web isn't just a structure. It's the universe's grandest symphony, a composition written in gravity, dark matter, and starlight across unimaginable scales. These 28 intricate patterns we've explored are more than cosmic curiosities. They're the fundamental architecture of existence itself, the scaffolding upon which galaxies are hung like ornaments on some celestial holiday tree. But what makes this web truly astonishing isn't just its scale or complexity, it's how radically it's transformed our understanding of the cosmos. Where we once saw random sprinkles of light in the darkness, we now recognize an ordered chaos, a delicate balance between vast emptiness and glittering nodes, all governed by laws we're only beginning to decipher. Consider how recently this revelation came to us. For most of human history, the night sky was a two-dimensional tapestry, stars fixed to some distant sphere. Even after Galileo turned his telescope skyward, revealing countless more stars, the universe still seemed like a scattered collection of isolated points. The truth that these specks of light are connected across unfathomable distances by invisible threads of dark matter would have seemed like pure fantasy just a century ago. Today, thanks to painstaking observations and revolutionary technology, we can map these filaments, measure their gravitational pull, and even simulate their formation from the universe's first moments. The cosmic web isn't just something we observe, it's something we've learned to see, a hidden reality now made visible through science's patient gaze. Yet every answer uncovers new mysteries. Why do some filaments remain stable for billions of years while others dissipate? How exactly does dark matter interact with the ordinary atoms that make up stars and planets? And perhaps most intriguingly, are there even larger structures waiting to be discovered beyond the observable universe's horizon? The cosmic web isn't a static map but a living puzzle, one that continues to challenge our most fundamental assumptions. Take the Great Attractor, for instance, a gravitational anomaly so powerful it pulls thousands of galaxies toward it, yet remains frustratingly hidden behind the Milky Way's dust. Or the cold spot, that enigmatic chill in the cosmic microwave background that might be evidence of a collision with another universe. These aren't just gaps in our knowledge, they're doorways to deeper understanding, reminders that the universe always has another card up its sleeve. What's truly humbling is realizing how deeply we're embedded in this grand design. Our Milky Way isn't some solitary wanderer, it's a single thread in the local group's tapestry, which itself is but a small knot in the Virgo supercluster's weave, all flowing toward Laniakea's unimaginably vast embrace. The atoms in our bodies were forged in stars that formed along these very filaments, their material cycled through generations of cosmic evolution. When we study the cosmic web, we're not just exploring distant realms, we're tracing our own lineage, following the paths that led to our existence in this particular corner of space-time. So where does this leave us? With wonder, certainly, but also with responsibility. We live in a privileged era, one where the universe's largest structures are still close enough to observe, their light not yet stretched beyond detection by the relentless expansion of space. Future civilizations, should they arise in billions of years, will gaze upon a far emptier cosmos, their night skies devoid of galaxies as the accelerated expansion carries them beyond the visible horizon. Our time is special, a window when the cosmic web's grandeur remains visible, its patterns still decipherable. As we close this journey through the universe's hidden architecture, remember that each of these 28 structures tells a story of gravity's patient work, of dark matter's invisible hand, of a cosmos far stranger and more interconnected than we ever dreamed. Which thread captivated you most? Was it the Sloan Great Wall's impossible scale, the bullet cluster's dark matter revelation, or perhaps the lonely galaxy adrift in the Boötes void? The conversation doesn't end here. Drop your thoughts below, and let's keep unraveling the universe's greatest mysteries together. And if you've enjoyed this cosmic expedition, consider subscribing for more voyages to the frontiers of space, where every discovery rewrites what we know about our extraordinary